Right. Hello everyone and welcome back to another IGCSE physics video where the code for the syllabus is 0625, extended of course. And in today's video we'll be looking at thermal physics. Now as per usual, I'll be following the order that's been presented in the syllabus. So do keep that in mind. The first thing on our agenda today is discussing the kinetic particle model of matter. Now, you only need to remember 4 points about the kinetic particle model of matter. And this being number one, matter is made up of tiny particles, and these particles can be called atoms or molecules depending on what substance you're talking about. Number two, the particles are in constant motion, and so by proxy, we can deduce that they have kinetic energy, which we discussed in the previous video about general physics. The third thing you need to know is that the kinetic energy of the particles can increase with it increases as the temperature of the particles increases, and thus you can say that the kinetic energy is directly proportional to the temperature of the particles. And last but not least, there are forces of attraction and repulsion between particles, and these forces of attraction and repulsion depend on the distance between particles. I haven't really written that down here, but basically the lower the intermolecular distance, the greater the force, and vice versa. And so thus you know the basics about the kinetic particle model of matter. The next thing that we'll be looking at in this video is the states of matter. Now, as we all know, matter can exist in three states: solids, liquids, and gases. And the main thing that we'll be looking at is the distinguishing properties between the states of matter and also their structures. Now, in the case for solids, you can see that the particles are very close together, so we say that the intermolecular distance is very small. And if you remember the fourth rule under the kinetic particle model of matter, the smaller the distance, the greater the forces of attraction and repulsion, which applies for solids. Also, a thing that you should keep in mind is that the particles in a solid do not only display vibrational motion, so they don't move about like the particles of liquids or gases. And thus, because they have strong intermolecular forces of attraction, they also have a fixed volume and a fixed shape, which is two of their properties. And on top of that, they tend to have extremely high melting and boiling points, at least compared to liquids and gases. Sorry. Now, on the other hand, we have liquids. Now, particles of liquids are further apart with less forces of attraction compared to the particles of solid. And the less force also allows the molecules of liquids to take the shape of its container, which is why we say that they don't have a fixed shape. However, the intermolecular forces are still strong enough to make it so that liquids have a fixed volume. Which is important distinction between liquids and gases. Another thing that you need to keep in mind is that the motion of particles of liquids is random and only within the container. Put a pin on that. I'm going to say something similar in a few seconds. Now we come on to gases. The molecules of a gas are very far apart, and thus the forces of attraction between them are really low or really weak, especially compared to solids. And this makes it so that they don't have a fixed shape or volume, and they can also be compressed. And the motion of the molecules of a gas are also random, and they are unlimited in the sense that they can go large distances without being confined. Whereas for liquids, whereas molecules of liquids are confined. So that's what I was talking about a few seconds ago. Right. Now the next thing that the syllabus requires you to know is the terms that are used for the changes in state between solids, liquids, and gases. If, for example, ice, which is a solid, becomes a liquid, or it becomes liquid water, we say that it has melted. That's called melting. Similarly, a liquid can become a gas either via evaporation or via boiling. They are not the same thing, and we'll be looking at the difference between evaporation and boiling later on in the video. On the opposite end of the spectrum, gases can also convert back into liquids via condensation, and liquids can become solids again via freezing. This is pretty basic stuff, I'm sure we are all aware, but it's still something that you need to know as the syllabus requires you to have some knowledge about them. Also keep in mind, melting, evaporation. We'll be looking at melting, evaporation, and boiling more in detail. We'll be looking at them in detail later on in the video as well. So, yeah. Right. So, the next thing that I want to talk about is the idea of absolute zero. Now, absolute zero is, theoretically speaking, the lowest possible temperature that matter can reach, where the particles have the least kinetic energy. Over here, I want you to recall that the kinetic energy of particles is directly proportional to temperature. So, if temperature increases, then kinetic energy also increases. And similarly, if you decrease the temperature, you can decrease the kinetic energy. So, in theory, there has to be a temperature where the kinetic energy of particles is at its lowest value, and this temperature is called absolute zero. And we actually have the value for absolute zero, that being minus 273 degrees Celsius. This is absolute zero. Yeah. I also want to emphasize a point that I brought up earlier on in the video. It had to do with intermolecular distance and the properties of matter. So, just a minute. Right. As I was saying, some of you might have realized back when we were looking at the properties in the states of matter, that the intermolecular distance and forces seem to have a role in determining their properties. So, for example, the reason that gases are able to move randomly and unlimitedly is because they have really weak intermolecular forces of attraction. And really, I just wanted to emphasize the fact that the changes in the intermolecular forces of attraction between the particles in matter, and thus causing a change in the distance between particles, is what creates differences in the properties between the different states of matter. That's a mouthful, but it's something that I just wanted to point out. Right. The next thing on our agenda is to consider the source of pressure in gases. So I'm sure we've all heard of the term gas pressure, and like all things made of matter, gases can cause pressure. But you must consider where this pressure comes from. And the best way to think about this is by imagining a container with gas molecules trapped in it. Now, these gas molecules are in constant random motion. So it can move like this, and then it can move like this. They move randomly, and thus they are likely to collide with one another, or they're likely to collide with the walls of the container. As you can see, this particle is colliding with a corner in the container. So is this particle and this particle. And this applies to all the molecules. The random collisions are likely to include some collisions against the walls of the container. Now, as one of the gas molecules collides with this container walls, there's going to be a change in momentum, which is, remember, change in P, and a change in P is just mv minus mu. And the rate of change of momentum that occurs, so the change in momentum that occurs per unit time would be mv minus mu over t. So as you can see, with every collision, a a gas molecule exerts a force, which is just mv minus mu. So, as a force is exerted per unit area by a gas molecule on the surface of a container's wall, it creates pressure. So, this force per unit area, let's say this, the force that occurs per unit area is the pressure caused by the colliding gas molecules. Colliding gas molecules. Right. And yeah, that's really it. That's the basics of how gas molecules can bring about pressure. The main takeaway here is to understand the relationship between change in momentum, force, and pressure. And yeah, that's about it. We'll also be looking at something called Boyle's law in a bit. In fact, we might have to look at it right now. Right. Before we look at Boyle's law, I just want to mention some of the factors that affect the pressure in a gas. So the first factor is volume. The volume of the gas. Right. And volume is inversely related to the pressure. Rather, I should say that pressure is inversely related to the volume in which particles are present. And you can explain this simply by imagining it. If I have a container and I have particles that are randomly moving about and randomly colliding with the walls of the container, as I shrink the volume, the same number of particles are going to occupy a much smaller space. So they need to travel a much shorter distance in order to collide. And so the number of collisions is going to increase, causing more force to be exerted per unit time, leading to, causing a greater change in momentum per unit time, leading to more force being exerted per unit area, causing an increase in pressure. Basically, pressure is inversely related to volume, and this is the basis of what we call Boyle's law. I'll focus more on Boyle's law in a few minutes. Let's look at the second factor that affects pressure, that being temperature. Right, temperature. Now, temperature is even easier to explain. Temperature is directly proportional to pressure. So, as you increase the temperature, the gas molecules will gain more kinetic energy, and thus they'll move faster and collide with more energy. And also, the number of collisions is likely to increase as they move faster, and this will obviously cause an increase in gas pressure. And with that, I think we can finally go more in depth about Boyle's law. So let's do that. Right. So over here we have Boyle's law. Now Boyle's law basically states that the pressure of a fixed mass of a gas, P, is inversely proportional to its volume, given that the temperature is constant. Now what that means, well, we explained what it means before, but as you decrease the volume that is occupied by the gas molecules, the pressure of the gas will actually increase, and that's the basis of Boyle's law. Now you also need to keep in mind that you can create an equation from this where P is equals to K over V, and K, which is a constant, is equals to PV. And basically, as per this equation, I can derive that the PV, or constant, it remains the same. So I can derive the equation P1 V1 equals to P2 V2. So if I have the same gas that, let's say, occupies 5 centimeter cubes at a pressure of 5 pascals, and I were to reduce the volume to 2 centimeter cubes, I could use this equation to calculate the new pressure of the gas. by simply making it the subject of the formula. And most of the questions about Boyle's law involve using this formula, which is why you should really make sure you understand it and take note of it. Now, another thing that you need to really make sure that you know is how to convert temperatures from Kelvin to degrees Celsius. Now, if I were to ask you what the SI unit for temperature is, I know that most of you might say degrees Celsius. That's wrong. The SI unit for temperature is actually Kelvin, and we represent Kelvin with a capital K. Of course, 1 Kelvin is really high in degrees Celsius. So in our day-to-day lives, it's impractical to represent temperatures using Kelvin, which is why we use degrees Celsius. But you need to know how to convert from Kelvin to degrees Celsius, for which you have a formula. So if I have a temperature, let's call it T, and this temperature is in kelvins, that's equals to theta, which is in degrees Celsius, plus 273. This might look confusing. We can confirm, we can figure out what this means via an example. So let's say I ask you to convert 5 degrees Celsius to something Kelvin. You could obviously use this formula, and you can just rearrange it to be a T, which is your Kelvin, is equals to 5 degrees Celsius plus 273. So 5 degrees Celsius is 278 Kelvin. And yeah, that's all there is to it. You just need to basically keep this formula in mind. This is the most important thing that you should take away from this section of the video. Right, so another really important concept that shows up a lot in paper 4, which is your theory paper, is understanding Brownian motion. Now, before I even explain what it is, I want you to think of an example where I have a petri dish with water, that's filled with water, and I just have some pollen grains in that water. Looking at this under a light microscope, I'm going to notice that the pollen grains are actually showing jittering, or they're moving about very short distances. And this random movement of the pollen grains is actually, well, it can be explained using Brownian motion. So let's figure out what it is now. Now, there are a few keywords that you need to use in your explanation when describing Brownian motion. Number 1, in this case, I gave an example of pollen grains. Sometimes they might ask you about smoke particles in air, and Brownian motion also occurs in that case. So you should be able to know when to use the term particles. You should know when to use the term particles and when to use something like molecules. So when you're referring to air or water, use molecules, and when you're referring to larger particles, you use particles. You should also use the term collision. If you try to describe Brownian motion without the term collision in it at least once, even if it's not there, you're probably going to be marked 0. This is a very important term you need to use. You should also remember the term random. Just saying collisions isn't enough, it's random collisions. So this is also an important term. And you should also use the term resultant force. I know as of now I haven't really explained anything. I'm just trying to, I guess, prep you guys. Right, so let me explain Brownian motion using my pollen grain example. Basically, the pollen grains are suspended in, the larger pollen grains are suspended in water which has smaller molecules. And the pollen grain particles are constantly being collided with by the water molecules, and the random collisions that occur between the two cause a resultant force to act on the pollen grains, causing it to move about randomly. And with that, that's all you really need to say about Brownian motion. Right, another thing I'll say is that the water molecules that collide with the pollen grains, well, I mentioned that they're small, they're also light in terms of mass. So you can say that the light, fast moving molecules of water collide with the larger pollen grains or particles, whatever. And yeah, so that's another thing that you can say, and that's Brownian motion done. Right, so the next thing that we consider under thermal physics is the phenomena of thermal expansion, which occurs in all states of matter, so solids, liquids, and gases. Basically, it describes how molecules of solids, liquids, and okay, let's consider solids and liquids first. Basically, over here, as you heat up a solid or a liquid, its particles gain more heat energy, and thus they move faster or they vibrate with a longer amplitude. In the sense that, for example, solids, when they gain more heat energy, well, usually they vibrate in this sense. But as you heat a solid, it's going to vibrate with a longer amplitude, and this is going to cause an expansion in the solid or liquid, or rather it's going to cause an increase in the volume, and this entire phenomena is called thermal expansion. Now gases also undergo thermal expansion, but the description of how it occurs in gases is a little different, where again let's consider gas molecules trapped in a container. So let's just do something like this real quick. As you can see, the gas molecules, they already move large distances and collide with one another, but as you increase the temperature and they gain more thermal energy, they travel faster over larger distances, and so they collide more they're likely to collide more and with more energy with the walls of the container. And as this occurs, as we described earlier in the video, the pressure is also increased, or the gas pressure also increases. But remember, pressure remains constant. To keep the pressure constant, the volume of the container must be increased. Essentially, you're employing the use of not Boyle's law, but you're still employing the use of the phenomena, the relationship between pressure, volume, and temperature. And basically, as the volume of the container is going to increase a little to account for the increase in the gas pressure. And this is how expansion occurs in gases. Now, another thing that you need to know based on the syllabus is that gases expand more than liquids and solids because the forces of attraction between the gas molecules is much weaker than that of solids and liquids, and by proxy, liquids also expand more than solids because the forces of attraction are weaker, at least compared to solids. And yeah, that's about it. Let's just look at the syllabus real quick. You have, yes, I have described everything that you need to know about thermal expansion. And now we can finally tackle, I would say, well, we can also look at some examples of thermal expansion, or rather some of their applications. A popular question is that of bimetallic strips. Basically, it's just two strips of metal, something like this. When you heat it up, these two metals are different, by the way, but as the temperature increases, the metal on the outside, which I've shaded in black, expands more than the one on the inside, so you get like a horseshoe kind of shape as that occurs. Thermal expansion can also be used in productive ways to prevent the sagging of power lines. So sometimes power lines are likely to sag like this. However, due to thermal expansion, you can cause them to be straight like this. It can also help fix gaps in bridges or railway tracks. And yeah, now finally, I think we're done with thermal expansion and we can tackle specific heat capacity. Well, now we can tackle specific heat capacity, now, or CHC. CHC is defined as the amount of heat energy required to change the temperature of a unit mass of a substance by 1 degree Celsius. Now, what does that mean? Let's say I have 1 kilogram, 1 kilogram of a substance. Let's say this is iron, and it's at 15 degrees Celsius. How much heat energy does this block of iron need to absorb before the temperature can increase to 16 degrees Celsius? And that basically just describes the specific heat capacity of a substance. There's a formula for calculating it, where CHC, whose symbol is just a small c, is equals to E, which is energy, over mass, which is m, times a change in temperature, or E over m change in theta. And change in theta is a change in temperature. So change in theta is just something like the final temperature minus the initial temperature. Right. Now you can also rearrange this equation to make energy the subject. So E is equals to mc theta, or mc change in theta, and this is a very popular equation that you need to keep in mind. It relates with electricity, and I'll explain that in a minute. But first, let's look at the SI unit for CHC. The SI unit, which is joules per kilogram Kelvin. Remember, the SI unit for temperature is Kelvin. But practically speaking, in almost all IGCSE questions, your answer is likely to be as joules per kilogram degrees Celsius. So the SI unit is joules per kilogram Kelvin, but most of your answers will almost certainly be as joules per kilogram degrees Celsius. Right. Now, we'll be looking at a small experiment for determining the specific heat capacity of water. Right? So this is the basic setup that you need when you want to try and find out the specific heat capacity of a liquid. So let's assume that this liquid is water. Some of the apparatus involved here are obviously a thermometer. So this is the thermometer. You have a voltmeter, which is this, an ammeter, a switch, a cell, and you just have this container is actually called a calorimeter. Let me spell that out. Calorimeter, or you can just call it a lagged container, or a lagged container, just container. What this does is it prevents most of the heat from escaping. Now, the main idea, right, there's also a stopwatch that's involved here. Let me just quickly draw that. And this stopwatch is used for measuring time. I know it seems like we aren't doing anything right now. It will all make sense in a bit. You have a stopwatch that you use to measure time. Now, we know that E is equals to mc change in theta, mc theta. That's especially when relating to heat energy, E is equals to mc theta. When relating to electrical energy, E is equals to IVT. This is a formula that we'll highlight again when we get to electricity and magnetism, which is section 4. But for now, just remember that E is equals to IVT. Now, because energy is the same regardless of its form, you can say that mc theta is equals to IVT. Before we get any further, let me just explain what's going on here. Basically, we have a circuit. This is our circuit that's heating up this water. And as the water heats up, the temperature rises, which we can record using the thermometer. And based on this formula, we can measure every single quantity aside from specific heat capacity. Now, what do I mean by that? First of all, we can measure the current due to the presence of an ammeter. The ammeter is it's an appliance that allows you to measure the current in a circuit. We can measure the voltage using a voltmeter. It's another appliance. Notice how the voltmeter is connected in parallel and the ammeter is connected in series. You'll learn more about this in electricity and magnetism. You can measure the time using the stopwatch. So you measure the time as soon as the switch is closed and as soon as the temperature of the water increases by 1 degree Celsius, you stop measuring the time. And as I just said, you can measure the temperature using the thermometer. And of course, you can measure the mass of water beforehand or before putting it inside the calorimeter. This leaves you with C, or your specific heat capacity, which is unknown. So you can just make C the subject, and using this formula, IVT over m change in theta, you can easily calculate the specific heat capacity for a liquid. And you can apply the same logic if you want to calculate the specific heat capacity of a solid. It's just that you wouldn't use a calorimeter. Right. You also need to know the value for the specific heat capacity of water. Most questions assume they require you to know it beforehand. So let me just write that down for you. So the specific heat capacity of water is 4,000, or it's approximately 4,200 joules per kilogram degree Celsius. Kilogram degree Celsius. And yeah, any conversions that you need to make. So sometimes in the question you need to give your answer as joules per grams degree Celsius. You can just make the necessary conversions from there. And with that, we are done with heat capacity. Right. So let me just review the syllabus real quick and make sure we haven't missed anything yet. Assuming we haven't missed anything, we can start with melting, boiling, and evaporation. And yeah, right. So melting, boiling, and evaporation. Melting, as you know, is a change of state from a solid to a liquid, and it occurs when you start heating up a solid, and that causes particles to gain more energy and vibrate more. And at a certain point, the energy of particles, so the kinetic energy of particles, is greater than the forces or the intermolecular forces that hold the particles in place. And this allows the particles to break free and or to break apart, and the temperature at which this occurs is called the melting point. And obviously this entire process is called melting. Boiling is very similar. So boiling is the change of state from a liquid to a gas, and again the concept is the same. As you heat particles more, they gain more energy, and eventually they gain enough energy to overcome the forces of attraction and see the change of state. The main thing that you really should know is interpreting a temperature time graph, where you'll notice that when melting and boiling occur, for a certain duration of time, the temperature remains constant. This is because the syllabus requires you to know that melting and boiling basically involve energy input without a change in temperature. Now what does this mean? Let's say I have a solid, ice for example, that reaches its melting point. So this is the melting point of ice, let's just say that. Once it reaches its melting point, all of the energy that I supply into it, I can continue heating it, but all of the heat energy that the ice particle or the water particles gain is being used to overcome the forces of attraction and see the change of state from a solid to a liquid, which is why for this duration of time, temperature remains constant. All the energy is being used to convert from a solid to a liquid. Of course, once a liquid is formed, which is at this point in time, it can continue to see an increase in temperature. However, eventually you also reach the boiling point of the liquid, where the same thing occurs, and all of the energy is being used to see a change of state from a liquid to a solid, and thus temperature remains constant at that point. Now we have to tackle evaporation, which is very similar to boiling. Basically, evaporation is a process by which liquids can convert to a gaseous state, which is how it's similar to boiling. However, evaporation can occur at various temperature ranges that are below the boiling point of that liquid. So, for example, if water were to convert to a gaseous state at 50 degrees Celsius, we would say that it has evaporated. But if it were to convert to a gaseous state at 100 degrees Celsius, which is its boiling point, we would say that it has boiled or vaporized. Now, there are huge differences between evaporation and boiling. And let's just describe those. So, evaporation only occurs at the surface. It only occurs at the surface. What that means is that if I have a container with water, the particles at the top of the container, which are the high energy particles, are more likely to overcome the forces of attraction and escape, leaving behind low energy particles. And going on a slight tangent, this phenomena also explains how evaporation can cause cooling, where I want you to recall one thing, which is that the temperature of an object increases, a rise in the temperature of an object increases its internal energy, and that an increase in the temperature of an object is related to the average kinetic energy in all the particles of that body. What that means is that as the high energy particles escape, you have low energy particles that are left behind in the container. And these low energy particles cause the average kinetic energy of the liquid to drop, thus causing a reduction in temperature. And so evaporation causes cooling. Another way that evaporation differs from boiling is something that I already mentioned. Evaporation can occur at all temperatures below the boiling point of the liquid, whereas boiling only occurs at a specific temperature. So you can easily see that in the graph, where boiling occurs at this temperature, that right here. However, evaporation can occur at this range of temperatures, which is another difference between the two. Also, evaporation only occurs at the surface and boiling occurs throughout the liquid. I forgot to mention that. And thus, evaporation and boiling differ in many ways. The next thing that we need to consider is the factors that affect the rate of evaporation. So those include, so some of the factors that affect the rate of evaporation that the IGCSE syllabus requires you to know, especially if you're doing this extended or supplement version, are number one, temperature. So an increase in temperature increases the rate of evaporation. I think as of now that's pretty self-explanatory, and the logic behind why should be understood by everyone. The second factor is surface area. So the greater the surface area exposed to air, the greater the surface area of the liquid, the greater the rate of evaporation. And that is to say that container B has a greater rate of evaporation than container A, even if they both contain the same amount of the same volume of water. And questions involving wide and narrow containers such as these are very common in paper 2, which is your MCQ paper. The third factor is wind speed. So the greater the wind speed, the greater the rate of evaporation. And the logic behind this is that as wind blows over a liquid, so as wind were to blow over this liquid, it could help carry some of the particles out of the liquid, and that would aid in evaporation. And those are the three factors that you must absolutely know that affect evaporation. Now, a few miscellaneous or rather notes that I just want to discuss, or footnotes that I just want to discuss, are number one, if an object that's in contact with an evaporating liquid also is also affected by its cooling effects. What that means is, take the surface of your skin for example. When it's hot, you sweat more, and this sweat evaporates. And as it evaporates, it also takes some of the heat from your body with it, um, and which is why your body sweats. It's to cool your body. So that's a thing that you should know. You should also be able to uh, you should also be able to describe condensation and solidification. Solidification is the same as freezing. Let me write that down. Solidification is the same as freezing. So the explanation behind these two terms, behind freezing and condensation, are just the opposite of melting and boiling. So I won't really go too much into it, but you should know both of them. You should also know the melting and boiling temperatures for water at standard atmospheric pressure. Standard atmospheric pressure is 1 atm. So at 1 atm, the melting point for water is 0 degrees Celsius. So ice melts at 0 degrees Celsius, MP. And the boiling point for water is 100 degrees Celsius, again at 1 atm. So that's BP. So you should know this. The IGCSE syllabus requires you to remember these two values. And with that, we are done with melting, boiling, and evaporation, and we come to the transfer of thermal energy. So we are almost done with this section, and yeah, we are at the tail end. Right, and so we come to the last topic, that is in thermal physics, that being heat transfer or the transfer of thermal energy. They mean the same thing. Now, heat transfer can occur via three ways. The first method that we consider is conduction. Now, conduction is most prominent in solids. So it's most prominent in solids, and it can occur in two ways. That is to say that you can consider it in two ways. Number one, if I have a solid and I heat it, let's say from this direction, the particles that are closest to the source of heat are going to gain some heat energy and vibrate with a large amplitude. And as these particles vibrate, they are going to make the particles adjacent to them vibrate as well. And this process will continue throughout the solid, causing heat energy to be transferred between vibrating particles. And this method of conduction can be observed in both insulators and conductors. The next, form of conduction only occurs in conductors. So, for example, a metal, metals often have a sea of delocalized electrons as part of the lattice structure, and these delocalized electrons are capable of carrying heat energy throughout the solid or the lattice structure. So, in addition to this first method, metals can also see conduction occurring through their delocalized electrons, whereas insulators only experience number one. And that's a thing that you must remember. Another thing, you should be able to obviously describe both of these, which I just did. And in terms of particles, you should be able to state why thermal conduction is bad in gases and in most liquids. Basically, the logic behind this is that because the particles of a gas are far apart, you can't really see conduction in them. And also, they don't have free electrons. And the same can be applied to most liquids. And yeah, that's about it. And obviously, because conductors can experience conduction in two separate ways, we can say that they're better conductors of electricity, or rather better conductors of heat than insulators. And that's conduction done. Right. Convection is most prominent in liquids and gases. Basically, it occurs in fluids. which is just the term that you can use to describe both liquids and gases. Basically, if I have a container or a room with fluid particles in it, and they are heated, so as the temperature increases, these particles are able to spread out more, or they are able to travel larger distances due to the extra energy that they have. Some particles are likely to gain more energy than others, so this will result in this is going to result in cooler particles sinking to the bottom because they are denser, while hotter particles, which are less dense, will rise to the top. And as these hotter particles rise to the top, they're likely to cool, while these ones are likely to heat up. So you're going to see something called a convection current, where particles move from least dense areas to more dense areas. Let's just look at the syllabus, where you need to be able to know how to know that convection is an important method of thermal energy transfer in liquids and gases. We've stated that. And you should also be able to explain convection in liquids and gases in terms of density changes and describe experiments to illustrate convection, and we have just done that. So now we can finally move on to radiation. Now, radiation is a form of heat transfer via EM waves or electromagnetic waves. You'll learn more about these in section 3, but for now you just need to know that all objects, that thermal radiation is just infrared radiation, and all objects radiate or they emit this radiation. And heat transfer by thermal radiation doesn't require a medium, which is why heat transfer in space is almost entirely done by radiation. So imagine this is Earth, or rather this is the Sun, and this is the Earth. Heat reaches from the Sun to the Earth via radiation, as both convection and conduction require material mediums to occur, while EM waves are capable of traveling in a vacuum. Another thing, EM waves all travel at the speed of light. You'll learn more about this in the next section. You should be able to describe some of the factors that affect the rate of radiation. So I would say there are 3 factors. Number 1, you look at the color and the texture of the surface. Color and texture. You are mainly considering white and shiny objects and black and dull objects. So black and dull surfaces are good absorbers of heat and good emitters of heat, but they are bad reflectors. While white and shiny surfaces are good reflectors of heat, but they are bad absorbers and emitters of heat. Now, you should remember that emission is not the same as reflection. Emission is essentially giving what you have into the world, while reflection is sending back what the world has already given you. That's the best analogy I can come up with. And an easy way of remembering the relationship between black and white is good emitters are usually bad reflectors. So good emitters, like black and dull surfaces, are bad reflectors, and vice versa. The second factor that you need to consider is temperature, which has a positive correlation with the rate of radiation. I think that's self-explanatory. Temperature. And the third factor is surface area, which also has a positive relationship with the rate of radiation. And these 3 factors are very important for you to know, because there are a lot of questions in paper 2 on these, and hence you should know them. Again, looking back at the syllabus, you should also know that for an object such as, let's say, object A to be at a constant temperature, let's say at a constant temperature of, for object A to be at a constant temperature of, let's say, 5 degrees Celsius, it needs to transfer heat energy away from itself at the same rate that it receives heat energy. So if it receives heat energy here, and I wish to keep object A at 5 degrees Celsius, so there should neither be a decrease or an increase in temperature. I need to see an equal transfer of energy away from object A. You should also know what happens to an object if the rate at which it receives energy is less or more than the rate at which it transfers energy. So that should be pretty self-explanatory to figure out from here onwards. And finally, you should know how the temperature of Earth is affected by the factors controlling the balance between incoming radiation and radiation emitted from the Earth's surface, which is uh, just these three factors, but in a more practical, but they are involved in a more practical sense. And with that, we are finally done with thermal physics. Well, okay, no, I lied. Beyond, there's some more, which is embarrassing, but okay. Uh, the last thing that you really need to take into account is heat transfer in a more practical sense. So, for example, if I have a frying pan, the handle, the main part of the frying pan is likely to be made out of a metal because metals are good conductors and they can conduct heat energy or carry out heat transfer in two forms of conduction. Uh, and the handle is likely to be made out of plastic or wood because that's a good insulator of heat and it helps protect your hand. Something else like a room with an AC or a heater is likely to see movement of particles depending on what you need it for. So ACs are often placed at the top as the cool air, and the cooler air which is denser sinks to the bottom where you are, so you can feel it. And the same application can be carried out with heaters. The only difference is that heaters are usually placed at the bottom of a floor, so it's the opposite of an AC, if that makes sense. With a fire, for example, you can actually observe. I'm putting my drawing skills to the test, but with a fire, you can observe radiation. Well, you can't observe it, but radiation occurs as a form of heat transfer with the fire. Also, convection occurs as the air around the fire is heated up. And also, up to some level, conduction can occur if you use the fire to cook something. Or if you use the fire to, roast something. And so finally, I can say that we are done with section 2, thermal energy. Like always, I hope you at least took something away from this video, and at the very least, you know what to revise for your upcoming exams. And thus, thanks for watching. Maybe consider subscribing if you like the video, and I'll see you on the next one where we tackle wave physics, which is a beast of its own. So, bye.